Yeah, I'm very happy to talk have this opportunity to introduce the research has been done by the MIST group. Most of the time, I'm working remotely in Hampton. I visit Blacksburg more often than I used to be, and I hope I can definitely visit more Blacksburg. So today's topic is called Enhancing Geospace Observation with Autonomous Magnetometer in Antarctica, a Global Context and Validation. And I'm Zhonghua Xu. I'm also a faculty at a space at VT, but mostly I'm located in Hampton. So what's in this presentation? First, we will talk about who are we, and then talk about what we do, and then why we pick Antarctica, not Blacksburg, and what is deep field instruments, and how we develop them, how we deploy them, and then what's the future, then with a summary. So first, I want to introduce the whole team, and the foundation of the team was built by Dr. Bob Clower, and some of you may know him. He and Dr. Weimer, located in Hampton. We used to have an office at the National Institute of Aerospace. Yeah, and Dr. Hardinger and Dr. Human used to work for the group. Now, Dr. Hardinger moved to SSI, and Dr. Human Kim become a professor at NJIT. And me and Shane just graduated this year, so he become a research faculty in the group. And I'm Zhonghua Xu, and our group is called MIST, stand for Magnetosphere Ionosphere Science Team. So the major science topic we're going to study is how magnetosphere and ionosphere coupling and all the physics behind that. So what do we do? I usually call myself a magnetometer guy. So on the left, this is a picture of the flush-gate magnetometer sensor in Antarctica. So that's me. Digging the snow, trying to adjust, just like connecting the cable and adjust the calibration. So that's during one of the trips I had to visit Antarctica. And why we're doing this? So I'm trying to get observation, get the information, and that actually relate to a new science topic, a relative new science topic called space weather. That actually protect our modern society. So why Antarctica? That all start with the Earth's magnetic field. So the Earth have its own magnetic field. Is very important because this field is acting as a shield, shielding lots of impacts actually from the sun. The sun keep blowing plasma into the halosphere, also is called a solar wind. So it carry billions tons of hot plasma and many particles and energy in it. So when it got close to the sun, it interact with the Earth's magnetic field, and this part we call is a magnetosphere. So some of the energy actually get into the Earth, but a lot of them are shielded by our magnetosphere, magnetic field, which protect us from damaging our atmosphere, from damaging the life, basically the life on the Earth. So that's one of the reasons we have life on Earth. So now we have more to protect, because we're using lots of satellite communication, navigation. Also, we explore more space. We have human activity out there. Also, aviation goes through the polar region. And also this can impact ground-based communication and the electric power grid. And it's not all bad. Sometimes we can see this great phenomenon called aurora, but that actually indicating lots of energy dumping to the Earth's magnetic field through the magnetosphere, ionosphere coupling with the solar wind. Okay, so this is now called space weather. So we need because lots of our modern society are depending on those electric magnetic devices. So this become more and more important to our modern society. So one of the reasons we went to Antarctica is currently we have lots of observation in the northern hemisphere. And this is one of the phenomena they found many years ago, that what they found is the aurora feature are kind of similar as well as different in both hemispheres. And it is supposed to be connected with the same magnetic field line. And in this case, we call it magnetically conjugate. So that means one field line connects with two spots on each end. So if we have observation in both ends, we can understand how those electrons' energy transport into the two different parts of the hemisphere, how the energy distributed. That can reveal us the secret of those energy and particle transportation. And that can help us to understand the whole dynamic of this magnetosphere-ionosphere coupling. Okay, but actually we don't have as many observations as in the Antarctic or the southern hemisphere to the northern hemisphere. So this is one of the reasons we put instruments, autonomous instruments in Antarctica. So this is a big map. So what we see here on the top is the northern hemisphere, okay? This is a Greenland. So the Denmark and the other international institutions, they build those magnetometers along Denmark and Iceland and through Svalbard. So they have a two-dimensional observation in the northern part, in the high latitude, or you can call it a polar region. But in the southern hemisphere, the autonomous magnetometer chain basically built by the MIST group is this one. And also we collaborate with the NGIT group. They have some more magnetometer distributed along here. So the MIST group magnetometer, we call it LPIP. I will have more details, but for short, we call it Penguin. That's why PG. So PG 0 to 5 are the currently operational autonomous magnetometer. They are magnetically conjugate. That means if I have a magnetic field line going from the north all the way to the south, we connect to one point here. So supposedly PG0 is conjugated to UPN, PG1 is conjugated to UMQ, so and forth, okay? And then now we're collaborating with Denmark, UK, and China, trying to build another chain along this one and also expand this one along that way. So we will have a two-dimensional coverage in both hemispheres. And some of them are actually conjugate. So if this dream becomes true, that will be the very first two-dimensional magnetically conjugated magnetometer observation network that covers the polar cap region, the polar Kasper region, and the some aurora region. So that's a very important dynamic region we need to understand. So those observations will be invaluable. Okay, so this is what we already established. So this map, actually, we mapping all the stations from West Greenland using that magnetic field conjugate thing, project them to the southern hemisphere. So you can see the PG1 is conjugated to UPN. The projection is very close to where the station is established in Antarctica. So that's actually, we did the mapping, we did the calculation, then we're trying to install the magnetometer close to that location. So, but this is not easy. The very first station is actually PG1. That was built in 2008, but there was some like a repair and others, so it's actually operational since 2009. And the very last one is PG5. That was in operation in 2016. So it takes us almost 8 or 9 years to build those 6 stations. And that actually involves some of them have to be revisited, repaired. So nothing is easy working with Antarctica. I will talk about that more later, okay? So why we call it ALPIP is the whole name is Autonomous Adaptive Low Power Instrument Platform. So this is not only have magnetometers, but also other instruments. That's why we call it adaptive. And it's a very low power instrument. Why? Because we are in the literally in the middle of nowhere. So there are no continuous power supply. We have to use a solar panel and a battery. And those station was built from the support, started with this NSF grant, and later we have more grants supporting us. And why is called Penguin? Actually, the Penguin is short for Polar Experiment Network for Geospace Upper Atmosphere Investigation. So those magnetosphere, ionosphere, also called upper atmosphere, because their altitude is from 80 kilometers to several RE. So that's considered to be upper atmosphere. Yeah. So this is our up-to-date status. So this is in summer of 2024. All 6 of them, we have them operation, but now they are in hibernation because the sun has been set in Antarctica and the battery reservoir have run out of juice. So all the stations are in hibernation. They will wake up in late September or mid of October, depending on the temperature and the sunlight. So all of them, we have the data downloaded through Iridium connection, and the data is available at ece.vt.edu. That's our new website. As well as we're sending those data to Siemens website, NASA CEDAWeb, SuperMag, and CEDA Medical. That's for where we put our GPS TC data. So you are interested in those data, you can visit our website, contact me, or visit those related websites. So currently we have lots of going on in this part. So Dr. Humin Kim from NJIT also working with us. They are collaborating with KRU, that's a Korean. So they're trying to put more station into the polar cap. As well, they are trying to revive or repair, some of the AGO, that's their autonomous station. And for us, the Virginia Tech group, we are maintaining the operation of those 6 magnetometer system. As well, we're collaborating currently with China. We just deployed 2 more systems like JK1 and JK3 from the Chinese Innerland Traverse. This was installed in 2003, and they revisited them in 2024. Early this year, retrieved the data. But there's some malfunction of the system. So some part of the system are retrieved to Shanghai. And Dr. Shane Toyo and I will visit Shanghai probably at the end of October, trying to work with them to get those ready and redeploy them so that can cover those regions. You can see there are not much observation there. So making them up and running, get the valuable observation there is very important. And on this line, you can see the extension of this line actually to the PG1 and the South Pole. So we will have a chain available there. And also there is a Zhongshan station here, and they have Kunlun station. So JK2 is actually called Taishan station. So if everything works, we have 7 stations along this line. And along this line, we have 8. And also we're working with the British Antarctica Survey, trying to put the PG6 and 7 along this line. PG6 has been deployed, but the Antarctic, the UK people haven't got the data back. They need to visit the site, and also they have another chain along this line. So we're sharing data using international collaboration to share the cost and the human resource as well as boost the science outcome. So international collaboration is very important for our group, and that's very important for Antarctica research as well. Okay, so this is one example. Oh, Shilin, do you have a question? Yes, please.
Sorry for interruption, Zhonghua. Can you go back to your last slide?
Yeah.
Just
yeah. Oh.
Curious about
yeah.
Curious about the US-China APEP network. Are those like the green triangle on the cross or all from that network?
Yeah. Oh, the green part is the projection from the West Greenland. So all the stations in green are the station from Greenland. So they put in the background to show where are the stations they actually have conjugate part in the northern hemisphere. Sorry, I forgot to mention that.
Oh, yeah. Okay. Sorry. I thought that those green.
Yeah, it's a very good question. Yes. So the red part is where the station our operation is. So there are a very light colored green in there showing the station that actually conjugated of some of them conjugated to the Greenland station in the northern hemisphere. So you can see those parts are important for building this two-dimensional conjugate observation network because there are lots of stations in the northern hemisphere. Okay. And as we know, in the northern hemisphere, in the Arctic region, there are lots of ocean, no land. So that's probably the only place we can have this conjugated network. Yeah.
Yeah.
Thank you, Shilin, for asking the question.
Yeah. So the US-China APEP network is only referred to that few black dot, like the Zhongshan. Yeah, the three black dot. Which?
Oh, you mean the other? This is the Chinese and US-China collaboration. Okay. Yes.
So there are three of them, and they are not operational yet.
We have some data from last year.
Okay.
Yeah, but yeah, after the hibernation in 2003, those stations don't have any communication. And when they visited the station in the field, they checked the data. There are no data collected after hibernation. So that's why we asked them to take all the blue box, that's our control box, back to Shanghai. And Shen and I are working with them, trying to diagnose the problem, trying to revive them and get them ready for the next deployment.
Yeah. Okay, I see. Yeah, thank you for the clarification.
Yeah, no problem. Yeah, any question you can ask me. Yeah. And this is an example showing how much difference, like spatial coverage-wise in northern hemisphere and the southern hemisphere. So Dr. James Wigan produced those we call the equivalent currents analysis with the two-dimensional network. So what we see here is actually AE, AL, and MF, BX, BZ, BY, as well as the sim age, the following the speed and the density. So those actually provide us some background geomagnetic activity and the following condition. So basically, we notice there is a quick event, transient event happening during this day. What happens there using the technique developed by Dr. James Wigan, he converts the magnetic field observation to this equivalent current. So basically, they rotated the magnetic field by 90 degrees. That's just by BL-SAFAR. That's kind of the direction of the equivalent currents. So we can observe where the currents are and how they develop during disturbances, the transient event caused by the solving. But you can see in the southern hemisphere, we only have this LPIP station available and some of the British Antarctic survey stations available. So there are not much observation. So we were trying to do this comparison. It's really sparse observation limited our science outcome. But now we're working on building more station along, I think, this way. Yeah, and we will have more coverage on here, so we can have better understanding of what's going on in the southern hemisphere. Yeah, so this is a picture of the overall look. This is the main tower. So you can see on the top, the solar panel and the GPS antenna, reading antenna. And this was during the installation. So you can see in the background, there are several boxes and the vehicle. Yeah, and this is the power switch. So basically for this LPIP platform, we have flash gate magnetometer, induction magnetometer, and the cases dual frequency GPS receiver. And some of them have those ones, and as well as the HF radio experiment. And a quick summary is this is a 12-volt power system with a 6 panel. So 2 here, 2 there, and 2 on the back. And with a lot of battery. We have 16 lead acid battery as our reservoir. So during the summer, the whole operation could be under 20 watts. During the winter, we are in the low power operational. It only costs 3 watts. Okay. So the longest one, PG1, has been returning data since 2009. So this year, 2024. So we have almost 15 years of data. And we do not really need to revisit the PG1. So we just do some air survey to see how much snow accumulation there. And since this is Antarctic, it's very dry. Actually, the snow accumulation from last visit is up to here. Yeah. Okay. But doing this, we need lots of logistic support. At least we need like several people. So usually we have a very small team, like 4 people, because we want to reduce the overall cargo transportation need, and 3,000 pounds of science and field camping cargo, and camp there for 4 to 7 days. And sometimes we need to revisit the site, trying to do some repairment, upgrade, so that we call touchdown time. So basically a small airplane take off there and 2 people working on the system for 1 or 2 hours. So in the future, and which we currently collaborate with Chinese, they are using the traverse. So that's another way we're trying to explore if that will be more efficient. Okay. So those are the picture of all the sensors. So this is the GPS sensor. And there are another GPS antenna there. That's just for GPS, like a normal GPS for time stamping, for location information. But this is for the dual frequency receiver. So using this dual frequency receiver's antenna, we can get more detailed GPS experiments done. One of them is very important. It's called a GPS TEC. We can get that total electron content to understand the variation of ionosphere. Yeah, and this is the flash gate magnetometer sensor. That's the search coil magnetometer sensor, and this is the HF radio. So basically, it's just a short video. So we have in our 6 system, 4 of them have HF communication. So we can send in HF signal between them. And we used to have a station at the South Pole, so we can communicate between those stations to see if there are any signal loss between them. That show us there are some disturbances happening in the ionosphere between them. Okay, so this is a closer look of the sensors. So everything is big snow put in there, and we need to align the sensor along the magnetic field actually out there. So we use a model and a compass to do the alignment for the surgical magnetometer, then cover everything with the plywood. Okay, and this is the flush gate. And that's a closer look. You need to make sure everything is aligned with horizontal and vertical direction. And also we need to rotate the sensor to get the minimum X and a minimum Y measurement, because if they align correctly, the Y number should be very close to 0, because we want to measure the horizontal part. Yeah, so this is the main page. The blue box, we call the blue box. The reason is they are blue, and they are actually the electronic control box. So all the we have the single board computer in there, all the adapter connect to all the sensors, and some of the power supply to the sensor are down here. And this big battery box is also our power box. So the solar panel actually goes through there first and charge all the batteries, 16 of them, and then charge the main blue box and charge the sensors. Okay. Yeah, so you can see that's everything coming from, all the cables coming from the main tower to the box. Yeah, so we basically dig a deep enough pit to put all the boxes in there just for future retrievement. Because working with Antarctica, we need to make sure we can retrieve everything we put out there, just due to SCAR treaty. We cannot leave things behind, even including human waste. So yeah, every trip we need to bring back the human waste. Yeah. Yeah, there's another picture showing how people work there. We flag everything. We're trying to build everything nice. So when we retrieve them, we know where to find what we need. Yeah. And this is just one day after the cover. The wind, the snow drift actually cover everything. That's why we need to flag everything, because if we don't flag them, it's really hard to see where the cable was. You can still see some part of the cable, yeah, because we pass some snow. So that's another thing. If you have some snow not flat, they have a higher chance to accumulate more snow, because the snow accumulation will actually, bury everything. So we need to try to make sure, we pat down most part around our instruments, so that can extend the life of observation there. Yeah. So you see, this is looking at the size. This is probably the surgical magnetometer pit, which is 500 feet from the main tower. So it's way away from the main site. Yeah. So those two are ECE graduate students at that time, and Dr. Karthik, yeah, his last name is quite long. We call him Dr. V. He used to be Dr. Wayne Skill's graduate student. His expertise actually ionosphere modeling, and he went there twice with us. That's Karthik, and that's Robson. I think he graduates with a master's degree from the ECE department. Yeah. So those are our camping sites. Some challenges we're facing there is, although we have 24-hour sunlight, which is good, but it's hard to maintain your time schedule. You have to learn how to sleep during daylight. And sometimes you can see the weather is really bad. And this is not the worst weather, but you can see it's already hard to tell the definition between the sky and the ground. That actually makes the airplane, they cannot fly out to pick us up or drop us off during that condition. So sometimes we have to wait many days to get a good enough weather to fly out and fly back. Yeah. And we use some snow wall to keep our tent safe. And also working in that region is not only cold. I mean, the cold part is okay because we visit there in the summer, but it could be close to negative 40 degrees. And it's hard to use your hand, a bare hand, to deal with that. So we upgrade everything, use this big origin pane and use a T-bolt. So we don't have really use a small screws and screwdriver to do the work. That is quite important. And also we use this big cable and sunlight-proof cable, and also use this butterfly connection. Everything is trying to make things a little bit easier when we're out there. And also the altitude for those stations are, I think the lowest one is 8,700 feet. The highest one could be over 12,000 height. So we are in high altitude, low temperature. That means the oxygen is not so much. So up there, sinking is very challenging. That's why we have those easy to install and good-proof connectors, as well as we have very detailed instruction and training. So make sure, we don't do more damage than we need to do. That's a very important thing for deploying them. And that's Joseph Macon, another VP graduate student. That was Dr. Hyun Kim when they put in those batteries there. That's the major part of the weight, because each battery weighs like 80 pounds, with the package and everything there over 100 pounds each. So we need to carry 16 of them. So the majority part of the weight actually from those batteries. So we're trying to get, and also those batteries doesn't work that well during cold temperature. Like we cannot draw juice out them. But for the life of the battery, actually cold weather is good. That's why they have been working almost 15 years. We still can charge them, recharge them. Yeah. But that's actually limiting us to have 12 months of duration, because when it's too cold, we cannot draw battery power out of it. Another thing is how to get there. The transportation from the South Pole is actually to the remote field is done by this little airplane called the Twin Otter. And the Twin Otter, they can only fly for a round trip is about 500 miles. But actually the PG-5 is 500 miles away from South Pole. So that means they can only do one trip there, and they cannot fly back. And this is not only not carrying any cargo. So what do we need to do? I learned this when I started working with the whole thing. Like previously, when with the PG-1 and the PG-2, because they are close enough, they can actually make the round trip. Yeah, those things are close, within 200 miles away from the South Pole. But when I go further and further away, I realize, by mathematically understanding, you cannot just refuel yourself by using the airplane. You cannot just drop enough fuel there and fly back. Yeah, so we need to ask the USAP, the Antarctica, US Antarctic program, to airdrop lots of barrels in between, so they can fuel there and fly there. So that increased the logistics challenge a lot. Okay. Yeah, so this is either the fuel supply spot. This is 300 view. So there's nothing else, just us. Yeah, with airplane and some barrel buried there. So this is what you feel when you landed in the middle of nowhere. Oh. Yeah, I took this video the first time I fly out there, and frankly to say, I have no idea this is going to be a successful landing or crash. Yeah, but since I'm back here, so this was successful landing. Yeah, so there was some challenging there, and also working with this blue box. Oh, this is a very delicate instrument. You know, all the heart and the brain are in there. So we use multiple insulation. The very inside insulation is actually a vacuum panel using for satellite. So it's a very good insulation, but sometimes it could be too good because during the summer, the whole temperature can be changing from -80 to -30. But the heat generated by the single board computer as well as other adapters can be 60, 80 degrees. Because this is really good insulation there, all the heat will be locked inside there. So normally, you know, although outside could be -80, inside here, only -20-ish for lowest, but the increase in temperature can cause a problem. Okay, so we noticed that we change some of the operation mode. So we try not to run all the sensors at the same time with a high frequency data collection mode. That helps us. So there are also things we learned, you know, during the last decade-ish. And another thing is they are very remote. I talk about the weather. So the good weather is like you working in the park, you just camping. But the wet weather, especially windy weather, is challenging. And also there have something called all white. So this is not all white. If it's all white, you just see everything is white because the snow blowing. So in that kind of condition for human being, will also depend on our visual sensing. So we will lose the conscience of direction. So you will easily get lost if you are not tied to some tent or somewhere. It's really hard for you to tell the direction. So we need to do lots of training to learn how to deal with the severe weather, you know, low dangerous thing there. Yeah, so we use this top wall to protect us from the wind, so we can work there. Yeah, so that's how we get there. So from Norfolk, Hampton, we fly to Los Angeles, Christchurch, and there could be connections. So that's like a 40-hour airplane and airport traveling. And then from there, we will fly 8 to 12 hours, depends on the wind and the weather condition, use a LC-130 airplane to get the Magnetometers station. From there, we will fly with another smaller airplane or LC-130 or DC-3 to South Pole Station. Yeah, and sometimes the weather is too bad. We have something called a boomerang. So we fly halfway through there and they tell us, oh, the weather is too bad. You cannot land here, so we'll have to fly back. So we call it boomerang. Yeah, so that's kind of interesting experience. And this is one of the interesting video I want to share here. That's a Karthik prepares our land.
Yeah.
So that's kind of showing how cold it could be out there. That's an English muffin.
Yeah, go down the video.
Okay. Here we go.
So it's a native orchid outside.
Yep.
Yep.
So the muffin is very hard frozen. And this is our mountaineer, also our site manager, usually taking care of make sure we can survive this windy weather. Yeah.
Yep, that's our lunch.
Yeah.
Okay. So those are more picture like how we work there. Sometimes we need to climb up this 9 feet high tower to install things, usually in a good weather. And sometimes we do get stuck. So one time we got stuck out there after we finish everything, installation and the operation, everything is operation, but we cannot get out because of bad weather. So out there, one thing is you are your own body heater. So you have to do some exercise or working on something, and keep eating and drinking, so your body temperature can maintain normal. So we use some spare time to build an igloo. Yeah, just you can also wait there and sit in the tent. Yeah. So after all this hustle, this is the most important, one of the most important outcome is the data. So all these data are available on our MIST website, including the flash-gate magnetometer, the induction magnetometer, and the GPS dual frequency measurement, that including the scintillation data as well as TC data. And some of the HF communication experiments data are also there. Okay, so this is a quick look. This is the summary plot of flash-gate magnetometer. So they have 3 components. This was taken at PG3, one of our site. This was on January 19th, 2013. You can see that 3 components. So the east components are very close to 0. That's why we need to do the calibration to install them that way. And this is the normal field. So you can see it's quite different between the H component and the E component. Yeah, so this is why we install them in inter-hemisphere conjugately. So we can see there are some similarity from all the red curve, that's the station from the southern hemisphere. Those black curve are stationed from the northern hemisphere. There are definitely some similarity and difference. So those actually can show how the physical process are different in the two hemisphere. So we did lots of study on this. We call inter-hemisphere comparisons. And those are the surgical magnetometer data, also called as induction. So what are they? They have lots of coils in a tube. So they can enlarge the change of even a tiny change. They can enlarge that change, but majorly they will see the dVdt, like the change, okay, in high frequency domain. So usually we use this power density spectrum plot to look at where the frequency they have more disturbance, when they happen, and how they happen from one station to another one. So some other study we can do is this kind of similar to James Wiggins' equivalent current study, but Dr. Kim Kim used this one to study the traveling convection vortices. Yeah, so they relate to the EMFC wave generation. And this is the GPS analysis done by Dr. Shija Deshpande. Now she's a faculty at the EMRAU University, and this was done. He developed this model to analyze the power and the phase scintillation we recorded, in the dual frequency cases GPS receiver. Yeah, that relate to the ionosphere change irregularities that can cause problem for satellite communication with the ground and also like GPS navigation. Yeah, so this is the HF radio data we record there. So normally they will be they are actually coded. So when some of the code are missing, there's some disturbance happening. So those dots actually showing there are some disturbance happen. So also we check with KP, DST, and the IMF following the proton flux. So to see the geomagnetic activity and the solving condition to see how they related to the disturbances in the HF radio communication. Yeah. So this is a very important, not directly applied to the scientific research, but important for operational function. So this is a housekeeping data. So that's the voltage change, that's the load of the CPU, and also other parameters we have been monitoring all years long. So this is important to understand how those autonomous systems work out there, how we can develop the next generation, and then the software component, and the server component, and that's the diagram how we do multiple system with the Iridium connection. And now let's talk about some of the scientific topic. So one of the important topic why we do everything is just based on the science need. So one thing we do is inter-hemisphere asymmetry study or comparison. So I did some study on the IP shock, and Dr. Koigo did some asymmetry on ionospheric conductivity during solar wind eclipse. That happened actually, the total eclipse happened in the polar region, Antarctica. Yeah, so we did that observation, and also Dr. Shi did some PC5 ultra low frequency wave study with multiple observation. And also we studied the solar wind magnetosphere ionosphere coupling. So everything actually, all the asymmetry study not stand by themselves. The reason we have those things is because they're showing the coupling process from solar wind to magnetosphere then to the ground, ionosphere. So we have some collaboration with many scientists domestically and internationally. So I only show a few topics here. So this is one of the examples that did by Dr. James Wigan. So in this disturbances, that's the thing we showed before, right? We monitored there was a transient event showing the solar wind, and we capture those changes in both hemispheres. And we find that some new asymmetries is showing that the responsible time are different between the two hemispheres. So in the future, which is not exactly future, some part has been already be done. So we trying to put more observation on this part so we can understand this phenomenon more better. Okay. And this is the IP shock study I did before. So basically, what is IP shock? That's called interplanetary shock. So basically, the solar wind can travel very fast. When they hit the Earth's bow shock, the front of the magnetosphere, they can generate shocks. So that's why we call it interplanetary shocks. When that happens, actually, the disturbances not only happen in the magnetosphere, those power and energy can be sensed on the ground. So majorly there are two types of the shock, depends on the impact angle. So on the left, this is the results on the ground, like that's what we call the geomagnetic disturbances response to the IP shock. So this is a tilted shock. That means the shock coming to the Earth's magnetosphere in an angle. So in this case, this kind of ideal case, this is almost 45 degrees. And this is we call the frontal shock. So basically hit in up front. So you can see very clear kind of symmetric response when they hit frontally, and quite asymmetric response on the ground with this inclined shock. So we did lots of case study, all the cases available during our data coverage. We studied that. We found that the response time and the intensity are controlled by the shock angle. So inclined shock, one side got hit first, we can see the quicker response time as well, a little bit more intense response on that side of the hemisphere. But for frontal shock, it's quite kind of symmetric, but not always the case. Yeah. And there are some other study by using this is actually done by Dr. Humi Hin's postdoc. Now he's a researcher in Leno, and he did some mag plot and also a related simulation. Yeah. So this is another collaboration with Dr. Doa in University of Alaska Fairbanks. So in his she's actually using the beta-RS simulation of the space weather framework. So what she did, she trying to figure out what kind of conjugate alignment change during those transient events. So this is observed response on both hemispheres. This is the simulated response in both hemispheres. This is the north component, this is the east component. So we figure out, okay, those conjugate location not always controlled by just the fuel line between them. The location can be changed, but also it relates to the fuel line currents generated around them. So there are more following up study we want to do. Yeah, this is another result we did. This done by Dr. Shane Koyo with during that total eclipse, and he also follow up with a very high impact publications looking through lots of substorm and how they coincide with eclipse. So they're like the solar wind, those disturbances are impacted by the eclipse or the substorm, or which one contribute more? What's the correlation? What's the status characteristic we call them? So this is the very first time someone actually did that. So in the future, we're trying to build our system. They can operate 24 hours. 24 hours a day, 12 months a year. So we can have the full coverage. That's very important. So we're trying to upgrade the batteries, maybe using some other energy supply. And also remote communication-wise, this is very important because we need to monitor the operation. We need to download the data. So we want to explore other way than Iridium satellite, because Iridium satellite, the bandwidth is limited. Yeah. And also we want to reduce the weight, reduce the size, that for easier deployment. And also we want partnership with not just the geospace, but also geophysics, because they are also people going to those in the middle of nowhere to get weather information or glacier information. So our station maybe can collaborate with them. We call the co-location instruments. So this is a big future plan. Yeah, I think I'm almost run out of time, so I'm not going to all the details, but you can see international collaboration and domestic collaboration are important for our work. And yeah, a very good news, like this year, I'm the PI and Dr. Shane Koyo is the co-I of this newly awarded proposal called DAISY Track 1. So DAISY stands by, I think, Data Array Small Instrument Development for Track 1. So Track 1, we just needed to develop the instruments. So we use this opportunity trying to develop our next generation LPIC, but not only aiming for Antarctica. So we want to build this more adaptive, so we can put more instruments on it with a lower power consumption, but also we trying to have a possibility to co-locate not just geospace instruments, but also like weather instruments or seismic observations, working with other institutions. And this can be deployed not just Antarctica, but it could be in Alaska or anywhere they are cold weather and remote. Yeah, and also we can build this one for a smaller size, more simplified version to use for like domestically in the US. Like currently, there are actually not enough magnetometer observation in the US. Yeah. So there are lots of expectation for this projects, and Dr. Koyo, Dr. Michelle Sazzano, they are early career scientists. So we hope this one, like Track 1, and then there will be another 4 years for the Track 2 if we been successful. And we hope, during those 10-year development, Dr. Shane Koyo and other young early career scientists, they could be the leader for the next generation. And also we have the funding in this project to support the GRA and the postdoc. So if you are interested in working with Antarctic related research, you may join us, join this hands-on experience with developing instruments, and you can understand the geospatial study, from the observation point of view. So that maybe you feel that's interesting to build up for over this too. Okay. So this is one of the example that we trying to collaborate with other. This is the GNSS. They are using those data to study the glacier change and others, but we can collaborate them to do something else. Yeah, so this is one example, like for all our stations, we have GPS location measurements. So actually, those stations, they are not stationary on one location. The glacier shifting, so we monitor the shifting. So we are looking for to have other collaboration. And recently, like last year already, we have this geoscope workshop trying to raise the awareness of how important the geospace is a part of the polar research. And in 10 years, now it's like 9 or 8 years later, we're going to have this IPY. So we need to get ready for that. Yeah, thank you.
Unmute. Yes, I did. Thank you so much, Zhonghua. Round of applause.
Yeah, thank you. So I don't know if there are any time for a question.
Yeah, very, very shortly. Any questions here? We're kind of approaching. I'm good to hang out for a little bit. I don't see anybody kicking us out of the room here just yet. So.
Yeah.
I'll have to go in a minute, but I thought it was awesome that you can have one of those operate 15 years untouched. That's incredible for an environment like that.
Yeah, thank you, Scott. And also for this newly awarded projects, I need to talk with you to about more details. I think this is a good opportunity. Yeah.
All right, let's do it. I'm interested to hear more.
Yeah.
Will you be adding more stations? You said the new program will upgrade the ones you have, but do you have any intentions to add more?
Currently, the logistic challenge is hard. Like NSF cannot support any new deployment in the next 3 or 5 years. But that's why they funded us to build the next generation system. But we work in international with the UK and China. So they are going to deploy our system.
Ah,
Yeah.
that's interesting. That's great.
Yeah. Yeah. Yeah, but this DAISY project is over like 2 million. It's not as big as the NASA one, but this is a good opportunity for training the future workforce and actually grows a route in the Virginia Tech for doing those Antarctic projects.
That's a huge success. Very important.
Yeah.
Yeah, no, I'll be interested to talk more. I would like to hear about the batteries. To get a battery to last 15 years with those kind of temperature swings and all that, I mean, it's amazing. That's got to be hard.
Yeah. Actually the cold weather is good for battery life because during the whole year is basically just discharge and charge for one cycle. So the challenge for us is actually do the battery juice when it's really cold.
Yeah.
But still, yeah. Those are just we did some tests. Actually, this started with Michigan. We did some tests, and this is one of the batteries very reliable to us. So that's the battery we currently use. Yeah.
Okay, still very impressive.
Yeah, thank you, Scott. Yeah.
Yeah. Any other questions here in the room? Mike Ronomy was with us here in the room and had to run out, but said, congratulations. I'm sure we'll be in talks later. But any others online? Any other questions?
And you can send me emails if you have any questions. Yeah.
This was great. Thank you for doing it.
Yeah, thank you, Scott. Yeah.
And we'll conclude today for now. Thank you, Zhonghua, again. And we'll have another Space AT seminar here in 2 weeks. And we'll actually hear from Scott Bailey, Dr. Scott Bailey, who's was talking there for a little bit. So we'll look forward to seeing that here in 2 weeks. Thanks.
Yeah. Thank you.